Hey everyone, this is Dr. Walker. This is video 10C, Kinematics from Integral Calculus. Throughout this chapter, we've seen how we can derive some kinematic quantities from others by taking derivatives. Now, we want to integrate and see what that gives us. So we're going to be looking at two different types of graphs, the velocity time graph and the acceleration time graph, and figure out, well, if we integrate or look for the area under the curve, what does that tell us? Let's start with the velocity time graph. So what does the area under the curve tell us? The best way to see this is to look at this area under the curve and split it up into a whole bunch of very thin rectangles. The rectangles are going to have a width, delta t, sub n, because there's going to be n little rectangles. If we're looking for the area of one of these rectangles, it's going to be length times width. The length is the average velocity for that rectangle, and the width is delta tn. So the area under the curve is an average velocity times a time. We know from the definition of average velocity that if we multiply a velocity times a time, we do get a displacement. So the area for this little shaded rectangle, we can see that that area is going to be delta x, and we can call it delta x sub n because it's just for this nth rectangle. And that's going to be the average for that rectangle and multiplied by the time for that rectangle. Now keep in mind that the smaller the width of these rectangles, the more that the function here can be approximated as a straight line. And so the amount of the rectangle that is outside of the curve ends up equaling the amount that's inside. It ends up evening out the thinner that you make the rectangle. So if we want to find the total displacement, all of these areas, then we have to add up all of these little rectangles areas. So we can go ahead and write that down. And now to get a more exact approximation, we really want the delta Tn to approach 0. So this is more of an approximation here, but to get a more exact area, then we want to take the limit as the delta Tn approaches 0 of this sum. And we know, maybe we know, hopefully we know, that when you do take a limit of a sum, that we do get a definite integral. And the definite integral is going to be the integral from t initial to t final of our velocity function. We're calling it v sub x just because it's along the x direction. We're just dealing with one dimension here. But so there we have it. If we have a graph of v versus time, and we take the area under the curve, we integrate that velocity, we get position. And this should not come as a surprise because we know that if we differentiate both sides with respect to time, that we will get that v is equal to dx dt, which is what we saw earlier in this chapter. Let's use what we've learned here to derive one of the kinematic equations. We could derive all of them, but I just want to derive one just as a nice little example. So if we have a velocity time graph, how can we derive or show that this equation is true? So to do this, you can draw any kind of velocity time graph, but I'm just going to draw a curve that is a straight line, because a straight line is constant acceleration. And we know that the kinematic equations have constant acceleration. So we have a velocity time graph, and we just learned that the area under the curve is going to be the displacement. So let's say that we want to know the displacement from this time here to this time here. Then we want to find this area under the curve. And we can see that we can break up this area into a rectangle and a triangle. So what is the area of each one? Let's go ahead and add it up. So delta x is going to be the orange area here. So how do we find that area? Well, from this time to this time, from this time initial to this time final, we know that the velocity changes from v initial up to whatever the final velocity is for that time interval. So the area of the orange rectangle, well, the length here is going to be delta t, which we usually just call t, if ti is 0, but I just drew it here for the picture, but we can always say delta t is t. And then the width here is going to be v initial. So the area of the orange rectangle is going to be v initial times time. And now for the magenta triangle here, we know that the area of a triangle is the 1/2 base times height. So the base here is once again t, but what is the height here? It turns out that the height is a times time. How do we know that? Think about it for a second. Think about what you know about the slope. The slope of a v versus t graph is a, right? The slope here is acceleration. Well, it's average acceleration, right? Which is delta v over delta t. So if you multiply a times delta t, you get delta v. That's what we're looking for here, right? This height here is delta v because it's from v initial to v final. So now that we have the height and the base of the triangle, we can do 1/2 base times height, 1/2 t times a, and delta t, we're just writing t. So we can see that we do get the kinematic equation. Delta x equals v0t plus 1/2 at squared. So this was an exercise using some calculus, but I find it really interesting to see how the graphs can actually give us those kinematic equations. Let's do a your turn here so that you can practice. We have another velocity versus time graph, and we want to find the displacement from 0 to 30 seconds. So go ahead and pause the video and calculate the area under the curve. So from 0 to 30 seconds is from here to here. So we want the area right here and the area right here. All of this area here. The area of triangle A is going to be 1/2 base times height, which is going to be 1/2. The base is 10 and the height is 20. So that's going to be 100. And then for B, we're going to have length times width, which is going to be 20 times 20, which is 400. So the total area, the displacement, is going to be the area A plus B. So we're going to have 500 meters for the displacement. The last thing I wanted to cover is what if we have an acceleration versus time graph? What does the area under the curve tell us? Now we could go through the same process and divide it up into a whole bunch of rectangles, but I'll save us that. and see if you can think. The velocity versus time graph gave us delta x. So what does this area give us? This area under the curve doesn't give us delta x, it gives us delta v. So we can write that delta v is equal to the integral from t initial to t final of the acceleration function. And once again, this should come as no surprise because we know that the acceleration function is the derivative with respect to time of the velocity. So the two equations, according to the second fundamental theorem of calculus, tells us that these two equations do go hand in hand.